Uh, Good morning, everyone. So I'm happy to give the first lecture on ocean ice sheet interactions. This morning I will give a very general introduction to this topic, and this afternoon Anna Wallin will speak more about the observational side on this, and then we'll have two other lectures tomorrow. So as David and others last week, I'm going to first speak a little bit about myself, about what I did before and how I ended up studying ocean ice sheet interactions. I started doing physics in Paris. I studied hardcore physics like quantum mechanics, particles and these kind of things, very similar to Martin. But at the end, I was a bit fed up with that, and I wanted to change, and I went to ocean and atmosphere dynamics, and I did the second year of my master's in that. That was great. I mean, I did very good science in Paris for my master's, but then I wanted to live in the mountains and be closer to the glaciers, so I looked for a PhD in Grenoble. And I found a PhD on atmosphere, ocean, sea ice interaction, and I had to develop a coupled model to do that. My PhD was not very successful. It worked, I got it, but it was not very good, and the work with my supervisor didn't work so well. So I was pretty sure that I didn't have any future in academic research, but I was still young, and before doing something else, I thought that it would be nice to do one postdoc. And I went to Nouméa in New Caledonia to still study air-sea interactions, but under tropical cyclones. And that was great, both for my personal life and for research. I met a very wonderful researcher over there, and it was very good. But just before leaving to New Caledonia, I had met my partner, which was still doing a PhD in France, and that was quite far. So I came back to France after a bit more than 1 year. I went to Grenoble and had the chance to get a postdoc that was quite open, so I could do whatever I wanted. So I kept working on ocean-atmosphere interactions, but under tropical cyclones, but more from the ocean perspective. Then my partner, it's usually part of the equation, so that's why I speak about my partner. So my partner found a very nice postdoc in Stockholm, so she went to Stockholm. I stayed in Grenoble a bit longer, but then the only way I found at the time to go to Stockholm was to create a private business in France so that I can work from wherever I want. So I created a small business to develop parts of climate models, and I got funding from one researcher. It lasted for a bit more than 6 months. And then after, we both went to Australia. Very good postdoc as well. I was interviewed by Matt, in part by Matt and others, and it was great. I worked on tropical climate, monsoon, El Nino, and these kind of things. It was very good also. That motivated me a lot also for research. And then at some point, went back to France because I got a position to work on ocean, ice sheet, sea ice, atmosphere interactions. So that was it. So let's speak about ice shelves now. So I think that the first picture we have of an ice shelf, that's something that is drawn in the book that James Clark Ross published in 1847. It's about the expedition that they did 5 years before that. And their main motivation was to go to the South Pole. And that, don't ask me why, but the main motivation of everyone at the time was to go to the South Pole. And they thought that we could go by the sea, so they were going south. And at some point, they met this huge cliff of ice that was like on their way. So there were two boats. It was Erebus and Terror, the boats, the ships. And so they went there, they met the cliff of ice, and they started to follow it, but they couldn't go to the end. It was too long. They had to go back to the north before reaching the end of the ice cliff. So I think that's the first description we have of an ice shelf. For them, it was an obstruction because they wanted to go to the south, and so they quickly figured out that they couldn't go further than the cliff, and for them it was a huge problem, and that's why it was called ice barrier. So they called these ice shelves at the time were called ice barrier, and very quickly, so they were wondering whether it was floating or reaching on the ground, and after just a few days, they measured the bathymetry there, and with a quick calculation, they figured out that it was not possible, that it was resting on the ground, So immediately they understood that an ice shelf was a floating piece of ice. Okay, 70 years after that, approximately, the Ross Barrier, which was also called the Great Ice Barrier. You have the picture here. This is the Ross ice shelf. And this barrier finally became a gateway to the South Pole. And here you have the routes that Shackleton took in 1908. He returned just before reaching the South Pole. Then you probably know the story that Amundsen went there in 1911, and Scott and his mates reached the South Pole just a few days later and never came back. So at the time, it was not obvious that the Ross was a barrier, and it was actually a gateway to the South Pole, so it became not so good, this way of naming the things. So shelf ice was proposed by a Swede called Otto Nordenskjöld, approximately at the same time as people went to the South Pole. And it was quickly adopted by most German and English-speaking scientists in the following years. For example, Mawson named an ice shelf like this in 1914. And Wright and Priestley wrote a very famous book called Glaciology in 1922 that was really a reference at the time, and that propagated the name shelf ice among the scientists and explorers. And after the World War, they reversed. Shelf ice became ice shelf, and it became the standard name until now. Okay, then at the time there was also a discussion. You've seen talks about fast ice last week. So people were wondering whether ice shelf was formed by fast ice on which you accumulate snow and that finally become very thick, or whether it was glaciers that were flowing into the ocean and then floating for some kilometers on the ocean. But very quickly, as far as they explored the coast of Antarctica, they discovered that all the ice shelves were attached to glaciers that was grounded. So they kind of understood very quickly that an ice shelf is formed by a glacier that is grounded, that flows into the ocean, and that doesn't break immediately, that keeps flowing in the ocean. So how people knew about the thickness and so on about the ice shelves, the first method that they used during the early 20th century, they just used a barometer. They were just walking with a barometer on the ice shelf, and they were measuring the height of the ice shelf. So it didn't tell you whether it was floating or not, but if you were on a flat area, you could imagine that it was floating, and then kind of knowing the shape of the thickness of the ice shelf. A real revolution for what we know about ice shelf was seismic echo sounding. Basically, you go with more than 10 kilos of dynamite on the ice shelf. You just make a big explosion, and then you measure the reflection of the waves. And from that, you get a very good idea about the thickness of the ice shelf. And before the 30s, it was not clear that whether there was a connection or not between the Weddell Sea and the Ross Sea under the ice. And in the mid-30s, it became clear, thanks to this technique, that Ross ice shelf and Fitch-Noroni ice shelf were actually disconnected. And then the second revolution for that was probably in the 60s, where radar came and became usable for scientific exploration. And since the 60s, we have radio echo sounding, which is usually done by plane. And with that, you get a good idea about the thickness of the ice shelf, and you can see whether it's grounded or not. And I think that Anna will talk a bit more about this as well. So that's Antarctica as we know it now. So on this map, the contours here show the drainage basins. For example, here, all the ice that falls here, all the snow that falls here, is then flowing towards that direction. And the hatched areas are the ice shelves. Approximately 75% of the Antarctic coastline is occupied by ice shelves. Ice shelves are pretty big. 50 of them are larger than 1,000 square kilometers. And you have 20 ice shelves that are larger than Corsica. And this one here is approximately the size of France. So it's pretty big pieces of ice, but also many small ice shelves all along the coast. Okay, so you've seen in Matt's presentation last week that freshwater is very important. And as far as the Southern Ocean is concerned, that the most important contribution of the ice sheet is really the freshwater. I won't speak too much about it because Matt gave his presentation last week, but basically housing experiments have really shown the importance of glacial freshwater. So housing experiments is numerical simulations in which you put a lot of freshwater at the surface of the ocean that corresponds to some behavior of the ice sheet, and then you look at the consequences of that. And as a brief summary, and in general, because there are small regional differences, this additional freshwater reduces the formation of Antarctic bottom water. It's increasing the sea ice concentrations, and it's warming the water masses entering the ice shelf cavities. So here I just show some salinity and temperature and salinity profiles for the Amundsen Sea in different climates. That was adapted by a paper from Justine Caillet. And this is just to illustrate the importance of freshwater for the deep ocean. So let's look at the blue profiles first. So you have here temperature, salinity, and potential density. And you have an ocean that is stratified. You have a fresh layer on top of a saltier layer. And the fresher layer is cold, and it's warm at depth. And what you need to understand is that when you produce sea ice, you release brine. And if you want to have convection until the bottom, you need to overcome this stratification. You need to densify all these surface layers so that it becomes straight here and that you have convection. So every year, at the season where you form sea ice, you need to overcome this stratification. If you add fresh water, the stratification will be stronger and it will be more difficult. You will need to produce more sea ice before you are able to trigger convection. And that's what you see on this plot. The red is when you add fresh water, so obviously it becomes less salty at the surface, less dense, and this prevents convection. So it means that you have more stratification, so it's saltier at depth and warmer at depth. And in this case, just the fact of adding fresh water at the surface is able to warm the deep ocean by almost 2 degrees. So it's very important for the ice shelves and so on to have correct freshwater fluxes at the surface. Okay, so the first part of the presentation is about the origin of the glacial freshwater, and of course I will have to speak about the ice mass balance for this. And so that we all speak about the same thing, here you have the view of an ice shelf. So the ice shelf is the floating part. Here you have the grounded ice sheet, the bedrock, the ocean. And so the ice shelf is flowing, and sometimes it breaks and creates icebergs. There is one example here. And glaciologists often speak about the grounding line. The grounding line is the line that is between the ice, the ocean, and the bedrock. So this is the ice where the ice becomes afloat. Typical dimensions. So the grounded ice sheet is several thousands of meters thick. The ice shelf is hundreds of meters thick. The grounding line is thicker, and the icebergs is about the same. So this figure is not at scale. It's if I was putting it at scale, it would be completely flat, and we couldn't see anything. And the iceberg would capsize because it's stable only because I extrapolated the dimension. And to make a similar plot as what Martin showed last week, if you have a typical ocean of 500 meters, sea ice would look like this, and ice shelves and icebergs would look like this. So you immediately see that the ocean stratification will be more important for ice shelves than directly for sea ice, at least, even if there are feedbacks. Okay, and important also to know is that the ice is flowing. It has a non-Newtonian viscosity, but very important viscosity. You have an accumulation area, the grounded ice sheet. The snow accumulates, so you have a flow of ice into the ice sheet, and then because you have a surface gradient, the ice will flow, and it will flow towards the coast. And once you reach the ice shelf, it will here come to compensate the melt rate. So in steady state, this flow of ice is compensating the melt rate exactly. And then some of the ice goes to the front and breaks and forms icebergs. So this is surface ice velocity that were estimated thanks to satellites products. And what you show on this map is that really the ice shelves are flowing quite fast because there is no friction on the ground. And so typically ice shelves reach 1 kilometer per year at the front. Some of them, like Pine Island and Thwaites, reach up to 3 kilometers per year of ice advection. Okay, so if you care about sea level, the important quantity is the ice flow that is coming through this gate above the grounding line, because the icebergs and the ice shelves are already floating. So they float, so if you melt them in first approximation, if you neglect the effect of salinity and so on, you have no contribution to sea level. So basically, estimating the ice sheet contribution to sea level is looking at the imbalance between the surface mass balance and the flux above the grounding line. Typically, in an approximate steady state that would resemble the year before the 90s, you would have a surface mass balance. So surface mass balance, I probably have to define this. Surface mass balance is the net mass flux at the surface of the ice sheet. So it's mostly snowfalls in Antarctica with a little bit of sublimation and sometimes runoff that is coming from melt, but it's mostly snow accumulation. In steady states, you have approximately 2,100 gigatons per year that accumulate over the grounded ice sheet, and you have the same amount that go through the grounding line. And then there is no sea level rise from this. It's just no contribution. And that's probably quite accurate to believe that the ice sheet was in steady state before the 90s, because if we look at the estimates from paleoproxies of sea level contributions, so this is the barostatic contribution to sea level rise for the different terms. So barostatic is all the contribution that is not due to the thermal effect, thermal dilatation of the ocean. And so you have the glaciers, for example, in purple, that have contributed to sea level rise for a long time. But Antarctica, the one that is in pink, has been pretty stable. There is a big uncertainty on that, but we think that there was not much contribution to sea level rise before the 90s. Okay, and now, so if you take now 92, 2020, we are not anymore in balance, and there is 90 gigatons per year of discharge in addition to the steady state, and that gives a contribution to sea level rise, which is 8% of the global mean sea level rise over this period. If you look at the more recent period, it's increasing, and now we reach 12% of the total sea level rise that is explained by the imbalance of Antarctica. And if you prefer curves, time series, you have the same here. So this is the contribution of, this is the evolution of surface mass balance, so it's pretty flat. And this is the total contribution in purple, and in red it's the ice, the part coming from the ice dynamics. And you see that really the ice dynamics is what explains the imbalance of the Antarctic ice sheet. Okay, but now we are in the Southern Ocean Summer School, not on the sea level rise school, so you probably care more about the freshwater cycle of the Southern Ocean. If you want to look at the freshwater cycle, then the ice shelf is also a contributor. If the ice shelf melts, you put basically fresh water in salty water, and it will change the salinity of the Southern Ocean. So if you care about the freshwater cycle, you need to look at the balance between the surface mass balance over the entire ice sheet, ice shelves included, and the negative part, the part that will compensate this one in steady state, is the iceberg calving flux here, and the ice shelf basal melt rate that is here. It's melting from below. I don't mention surface runoff. It's melting at the top, and sometimes the meltwater refreezes in the snow, but sometimes it goes out of the ice sheet. But this part is extremely small. This one is extremely small in the present day climate, so I don't even speak about it. It's like 2 orders of magnitude smaller than the other ones. And you have also melting beneath the grounded ice sheet. That's coming in part from geothermal heat fluxes, but the majority of the meltwater from below is coming from the friction of the ice at high pressure, and this will warm the ice and create the glacial runoff. It's not very important for the mass balance of the ice sheet, but it can be important for the ice shelf basal melt rates, and Anna may speak a little bit about that later. Okay, if you assume a pre-industrial steady state, you can look at the number and try to give estimates. So I didn't put the uncertainty, but it is quite large on these numbers. But you have this amount of surface mass balance over the total ice sheet, and there is a bit more than half that is going as iceberg calving flux, and a bit less than half that is going as ice shelf basal melting. If now you look at the present-day observations, there is an imbalance. When the climate is warmer, you have more snowfall, so you actually put more mass from the surface, but you also melt a lot more, and you produce more calving. So in general, you lose a lot of mass, and this will contribute to freshen the Southern Ocean. And of course, if you lose this mass, the shape of the ice sheet will change. You will have a thinner ice shelf, and the front will retreat. That's a map of Antarctica from Davison last year. So the size of the circles show the mass that was lost by the ice shelves, and the color is red when there is a mass loss, and blue when there is a mass gain. And if you look at all the ice shelves, you can see that out of 162 monitored ice shelves, 71 have lost mass, 29 have gained mass, and for 62 of them, it's within the uncertainty we were not able to tell. So it seems that a majority of the ice shelves currently in Antarctica are thinning and retreating. So now I'm going to speak a bit more in the details about the ocean ice shelf interactions. Are there any questions on the first part? If not, I keep going on that. Yes? Yeah, so there is most of the changes, the ice shelf changes, are in West Antarctica. That's clearly visible even for the grounded ice sheets. That's where the grounded ice sheet is thinning. You have some signals also for like here. Also, ice shelf are also losing mass. That's where you have the most changes. The amount of warm water going under the ice shelf is increasing. And I will speak more about this tomorrow. So maybe I don't start to explain the mechanism, but basically this is the part that is warming from the ocean. And here it's also a lot of warming from the surface in the peninsula. Yes? No, so all these estimations are from satellite estimates. Yeah, so the basal melt. So the basal melt is a result of there are different ways to estimate it, but you can. The important thing is to look at the balance. So the surface mass balance is the one that is coming from models. It's coming from regional climate models that are quite accurate to represent the snow properties and so on. And then from the satellites, you can measure the speed, the velocity of the ice, and the thickness from altimetry. And then you can make budgets, and you can deduce the melt rates. Okay, let's go more about the dynamics of melting beneath the cavities. So if you want to make it simple, you have typically three kind of conditions in which you have ice shelf melting. You have what some people call cold cavities, some other people call it mode 1 melting. For those who are familiar with the mass, the water masses, it's when you have high salinity shelf water or dense shelf water. It's water that is typically at minus 1.9 degrees, which is the freezing temperature of ice. So if you produce a lot of sea ice, you will release brine, and you will cool the entire sea next to the ice shelf, and the water will be everywhere at minus 1.9 degree. You have what people call warm cavities or mode 2 melting, and this is where you have circumpolar deep waters entering into the cavity. So these are typically water that are approximately at 1 degree. And then you have another mode of melt that is more seasonal melt. It's that for most of the season you are in this condition, minus 1.9 degree. but you have the Antarctic surface water that occupies the cavity, and in summer, after sea ice melting, you stratify the water column, and this stratified layer of fresh water can get warmed by the atmosphere, and if it's deep enough compared to the ice shelf thickness, it can penetrate under the ice shelf cavity. So in this case, you have melting that is more at the front and that is seasonal. It's not through the entire year. So why do we have melting at the surface freezing point? So for the sea ice, Martin and Dirk mentioned a freezing temperature that was only a function of salinity, but actually you have also a function of depth, which is important for the ice shelves. And so basically, if you melt fresh water into salty water, the freezing or melting temperature is at minus 1.9 degrees at the surface in salinity, in classical salinity range. But if you go at the depth of the grounding line, it can go down to minus 3 degrees. So it means that if you bring water that is at the freezing point at the surface to the grounding line, it will be above the freezing point and it will melt the water. So that's how you have melting. But then the water will lose energy towards the ice, and when it will go up, it can be now under the freezing point, and it can do refreezing and form what we call marine ice. So marine ice is a kind of sea ice that is formed under the ice shelves. Of course, if you have water that is at 1 degree everywhere, it will be more than 3 degrees above the freezing point, and it means that you will melt everywhere. So that's typically glaciers in the Amundsen Sea, like Pine Island or Thwaites. And then seasonal melting, you are just like this during winter and kind of like this during summer, so you have melt rates at the front. Now about the circulation, if you put meltwater with zero salinity into water that is very salty, it will be very buoyant, and it will create a plume, a convective plume that will go all along the front like this. The properties of this plume is affected by melt rates and also by entrainment and mixing. This is a very important aspect of the plume. So the plume will be cooled and freshened by melting, but it will be the salinity will increase due to entrainment and mixing, and the temperature also will increase. It's very important because this temperature brought from below will also keep the melt rates high in this configuration. And Anna tomorrow will speak more about what's going on really at the interface between the ice and the ocean. Of course, due to Coriolis, if you have this kind of circulation, if you have buoyant plume that is going towards the top, it will turn on the left like this, and you will also have friction, and so you have this kind of balance where the velocity of the plume is going upward and toward the left in Antarctica. Tides are also a very important aspect of the problem. In some of the ice shelf cavities, the circulation is mostly explained by tides. Like if you look at Fitchner-Roney, most of the currents are coming from tidal velocities. Tides have many different ways to impact ice shelf melting. The first thing is that you can increase the mixing in the top in the plume because you always have currents that are going one direction and the other. It will create shear, it will create upward diffusion, and this will clearly affect melt rate. If melt rate is affected like this, it will also create a residual circulation, and I will speak a little bit about this later. And you have also mixing. Tides is very important for mixing, especially at the continental shelf, just in front of the ice shelves. And if you have a lot of tides, you will basically weaken the stratification that I've showed before, and this will affect the melting under the ice shelves. And so tides is a periodic evolution, but there is also a residual tidal circulation that can, in the case of ice shelf cavities, bring water masses into the ice shelf cavities. So it can be important as well. Okay, though I've shown the plume, the circulation that is created by melt rates, but I'm going to say a bit more about what it gives in terms of number. From ocean modeling experiments, you can calculate that if you melt 1 millisphere drop of water, that requires 0.3 terawatts of heat. you create a circulation in the ice shelf cavity that is much stronger than this 1 millisphere drop. In the Amundsen Sea, you typically create circulation that are 100 to 500 times more important than the amount of melt that you put. So it's a very important thing. And it means also that because of this circulation that is created by ice shelf melting, you will also have a lot of heat input in the cavity. And in this case, you have much more heat that goes into the cavity than what is needed to melt the ice. So it means that you have an outflow, basically, of warm water. So in this case, the ice shelf is not cooling the water here, it's actually warming the water here, and this can melt the sea ice if you have a circulation like this. Because of this very strong circulation, it means also that the water masses don't stay very long in the ice shelf cavities, and if you have ice shelf cavities of a few tens to hundreds of kilometers, like in the Amundsen Sea, the residence time of water into the cavity is typically a few weeks. You have other cases that are similar to that in the ocean. This is a plot that was done by Stommel in 1982. And it's a plot that he did to understand the circulation, the ocean circulation that was created by a hydrothermal vent. And in this case, he found that one sphere drop of circulation was driven by only 3 times 10 at the power minus 4 sphere drop of hot water from the vents. So it's a typical kind of situation that you can have when you put small amount of fresh water into salty water. If then you take a very large ice shelf cavity and that you have water that is not too warm, you will still need 0.3 terawatt to melt 1 millisphere drop of ice. But in this case, it creates a circulation that brings only the amount that is needed. So there is a balance between the two, and it means that there is all the heat that is going into the cavity will be used to melt the ice. So if you don't provide more heat at the entrance, it can happen whatever you want in the cavity. It won't be able to melt more because all the heat is already used. In this case, the circulation is quite slow, and the residence time of water in the ice shelf cavity can reach several years. Can reach like typically 10 years for Fischner-Roney. Ice shelves are also important for water mass transformations. This is a result that was published by Catherine Hutchinson last year, and this is a temperature salinity diagram in an ocean simulation without ice shelf cavity, and this is the same where there is a representation of ice shelf cavities in the ocean model. And what you can see on this plot is that you have a water mass that appears here. It's a water mass of ice that is below the surface freezing point, colder temperature, less than -2, and that are very dense. And these water are called the ice shelf water, and they are important for the formation of Antarctic bottom water. So ice shelf also play a role for water mass transformation in the Southern Ocean. So now I'm going to speak about icebergs, but if you have questions on the ice shelf circulation, maybe you can ask them now. Yes? Yeah, it's observed as well. Yeah, I just took this plot because I knew that it was there, but there might be similar plots from observations. Yeah. Other questions? Yeah. This one is a global, typically a global ocean model that is used in a climate model. It's an ocean at 1 degree. But so in this paper, she resolved only 3 ice shelf cavities, Fischner-Roney, Ross, and Larsen. But it's sufficient to form these water masses next to the big ice shelves. Other questions? If not, I switch to the last part of this presentation. So I'm now going to speak about ocean-iceberg interactions because it's also part of the thing. So I've shown that a bit less than half of the fresh water from the Antarctic ice sheet is coming from melt beneath the ice shelves, but a bit more than half is actually coming from iceberg melting. So it's also important to understand how the icebergs behave, how they melt in the Southern Ocean. So from modeling studies, we think that there is approximately 3,000 gigatons of iceberg in the Southern Ocean on average. The icebergs follow this typical law that is typical in geophysics, and the number of icebergs is increasing for small area of icebergs. So it means that you have a huge number of very small icebergs and a small number of very large icebergs. This is the percentage. So look at the things in red first. So in red, the diagram shows the percentage of icebergs for given ranges of iceberg sizes. So you see that you have approximately 75% of the icebergs that are between 0.1 and 1 square kilometers, and you have very few that are between 1,000 and 10,000 kilometers square. This is for the number, but if you look at the total iceberg area, so based on this law, you have completely the opposite. You have almost none of the total iceberg area that is explained by the very small icebergs, and most of the iceberg area is explained by the very huge iceberg. And it works also for the volume. Most of the iceberg volume in the Southern Ocean is within very big icebergs, not in the tiny bits of icebergs. So now we can look at what moves the icebergs. And this equation is probably quite similar to the equation that Martin introduced last week for the sea ice flows before the rheology. So you have, of course, you have Coriolis, you have the friction of the air, the friction of the ocean, the friction of sea ice. Then you have wave radiation. I'm not a big expert in that, but the way I understand it, it's a bit like a boat. If you have a boat, it radiates waves. This carries a bit of energy. And for the icebergs, it's the same. If the iceberg move in a way, this will create waves that will be radiated from the iceberg, and this will change a little bit the momentum balance. And then you have the pressure gradient. For the melting, you have basal melting, so this is exactly as under the ice shelves, except that it's kind of as under the ice shelves. And then you have also convection on the side, melting along vertical faces. And you have also a term that is quite important, is the wave erosion. The wave erosion, you can see it. If you look at the shape of iceberg, you usually see something quite specific at the range that is in contact with the ocean. And this is also an important term for the ice shelves. And of course, you have also a term, you also need to do the surface mass balance at the surface. So let's look a bit at the equations. So you will have to believe me here, but you can look at this paper if you want to know more details. Icebergs around Greenland, in the Arctic, and in Antarctica don't move exactly the same way. The icebergs around Greenland and in the Arctic are usually smaller, so they are more affected by the Ekman spiral, and so they will be more affected by the surface stress. In Antarctica, what we observed is that the icebergs mostly follow the ocean currents, and you can guess from that the atmosphere and sea ice drag often have a weak influence on the thick icebergs. It's not true for all the icebergs, but in general, it's a good approximation to neglect friction of the atmosphere and the friction of the sea ice and also the wave radiation. So if you neglect this, you only have the pressure gradient, Coriolis, and the friction by the ocean. So if you do a balance for the ocean like this, you have the geostrophic balance. So you assume that there is here no stratification in the ocean. And from the balance between pressure gradient and Coriolis, you get the ocean velocity. If you then calculate the pressure on the ice shelf, you have an ice shelf that will follow the free surface like this. And then you will have compensated pressure force on the side, and you will have also a basal pressure and gravity. These two forces will create motion of the iceberg towards this direction. That will then turn to be in balance with Coriolis. And then in the end, if you simplify a bit the arrows on this plot, you have this, and you have basically exactly the same balance as for the ocean. So you end up, if you do all the calculations, you can do it properly, you end up with exactly the same expression for the velocity of the iceberg and the ocean. And in a way it makes sense, because this big piece of ice, if you condense it, it will be liquid water here, and it has no reason to behave differently than the rest of the ocean. So it makes sense that the iceberg is in geostrophic balance in this case. If now you introduce stratification, it means that the pressure gradient will be explained by the surface, but also by the density gradients within the ocean, and I've shown examples of density gradients here. And it means that the effect of density will increase with depth, and then in this kind of situation you can reverse the current at depth. This is just for the ocean. If you go to really strong stratification gradients, very strong density gradients, you can even reverse the current and have, for example, westward current at the surface and eastward undercurrent. Now what's happening in this case? In this case, you need to take also into account the stratification. You need to take the stratification into account in the calculation. And it means that you, for the average, it will be like for the ocean. You will have an iceberg velocity that is the same as the average of the circulation here. Okay, but in this case, it will be different from before, because now you have a basal drag. Before, the ocean and the iceberg were moving in the same way, so there was no friction between the two in steady state. The two go together. But in this case, it's not possible. The iceberg velocity is on average the ocean's velocity, but at depth, the iceberg velocity is different from the current velocity, so you will have a basal drag. And this will modify the trajectories of the iceberg. So this is the case of weak ocean stratification, is a geostrophic balance. And this is the case where you introduce basal drag. So you have the ocean surface velocity like this, you have the ocean velocity at the ice base, and you have the iceberg moving like this. So the iceberg is moving like this, the ocean velocity at the base is like dragging the iceberg in this direction, and then you have Coriolis and pressure. So it will basically move the iceberg in a different way as the mean ocean velocities. Now this is the iceberg melt climatology. It was derived from a model in which Lagrangian iceberg were introduced. And then you can look at the freshwater flux from these icebergs. What you see is that icebergs really transport freshwater from the Antarctic margin to further in the Southern Ocean. So if you want to represent the freshwater in the Southern Ocean, it's important to account for this transport of freshwater by the icebergs. If you don't do that in a model, you need to make choices that are not necessarily very good, to like spread in certain ways or put everything at the coast, which won't be as accurate as this one. And it can be regionally important for the sea ice production. So putting all the fresh water here is not the same as spreading everything all around if you produce sea ice at this place. So this is a figure that was done by Anna, who is here, recently. This is the iceberg melt pattern depending on their origin. So, for example, on this plot, this is all the icebergs that are coming from Emery Ice Shelf. And if you just look at these icebergs that are coming from Emery Ice Shelf, you see that they follow the coast, they follow the coastal current, and then they move to the north. This place here, it seems that most of the basin have the same track. They all follow the coast westward, and then they go to this place, which is called the Iceberg Alley. That's the place where you observe the largest amount of icebergs in Antarctica. Most of them behave a bit like this, and it's only when you arrive in the Amundsen Sea that you have also the effect of the Ross Gyre, and then you have also a lot of melt rate in this region. But for most of the places, you can have in mind that the icebergs just go around Antarctica and end up in the iceberg area that is here. Okay, yeah, that's my last slide. So that's something that Martin mentioned already yesterday, but I wanted to mention this again. Icebergs, they also affect sea ice and polynya, and what's happening. So here you have so this is the Antarctica sheet in white, the Southern Ocean in blue, and then you see all these little white pixels are the grounded icebergs. So that's icebergs that, like in this case, have gone on the bathymetry, and like if you are on a boat and you go fast towards the beach, then you end up on the beach, a bit higher than the sea level, and it's happening. The same is happening for the icebergs. If you have that, this will completely block sea ice, and this will help the formation of land-fast ice. This is a result of a simulation by Pierre-Vincent Huot, the reference is here. And basically, this is all the land-fast ice that is created due to the presence of this grounded iceberg that prevent the sea ice from moving. And then these are the polynyas, and you can see that the polynyas are created just along the fast ice, and this is the sea ice production. And you see that most of the sea ice in this region, so this region is Adélie Land, most of the sea ice in this region is created within these polynyas that are created thanks to the grounding of icebergs. That's in a model. There is a lot to improve in these models and a lot to observe that we don't know, but that's the general idea that we have on this for the moment. And I will stop here. So if you have any question, you're welcome.